Hi everyone, today I will be talking about our work game on the generalization of instructional action understanding, which introduces a benchmark to analyze the generalizability of instructional action understanding models. This is a joint work by Junlong Li, Kuan Yisheng, Yansong Tang, Jing'an Bao, Kun Zhang, Jiwen Lu, and Jie Zhou. This work focuses on instructional action understanding problem, which we call IAU. We learn to understand what the actions are and when they happen. For example, action segmentation model understands the actions by dense prediction of each frame, and action detection model localizes each step. The limited generalizability of models remains a challenge to the deployment in real-world environments. Conventional model learns how to inflate bicycle tires, and the generalization challenge would be how to inflate car tires. In fact, due to potential environmental bias, the model might not be well developed in an out-of-distribution environment. To encourage models to learn transferable knowledge, it is desirable to benchmark their generalizability. Since the key obstacle to the generalization of instructional action is the distribution shift of action steps under different task categories, we propose a new evaluation strategy to benchmark the generalizability by evaluating the models with OOD tasks. OOD task categories are different from the training tasks, but they are reconstructed from steps of the training task. The figure shows how to construct OOD tasks by reassembling steps. Here we have 4 tasks in the training step. Then we pick some steps, prepare seasonings, remove intestines, brush sauce, and bake to construct an OOD task, roast chicken. We can also construct majorly as another OOD task with other steps. The lack of benchmark of IAU generalization motivates us to collect and annotate a real-world IAU dataset, GAN. On the top, we show the construction of the GAN dataset. Given an instructional video training set, we first separate the steps of the training tasks and generate task candidates. After filtering out the unqualified ones, we search for YouTube videos related to the selected tasks. As for the statistics, GAN consists of more than 1,200 instructional videos related to 116 unseen tasks. It is divided into 2 splits as counterparts of coin and breakfast datasets, and we name them GAN C and GAN B respectively. This figure of stat frequencies rate shows the insights in the data. Stats distributions of the coin training and test set are similar, but they are different from the one of GAN C. We further propose a simple yet effective approach to enhance the OOD generalizability by performing causal inference. We first construct a causal graph and introduce context bias C. Note S and Y are step and prediction. The arrow denotes a link from cause to effect. Since this simultaneously affects the step and the prediction, we call it a confounder, and it misleads the model to spurious correlation. For example, in the task, inflate bicycle tires, using bicycle pump is always observed together with the step installing the nozzle, which brings excessive dependency. We write the likelihood with Bayes' rule and show that the likelihood is influenced by the probability of Z conditioned on S. We use an example to show that this probability is biased. When Z using bicycle pump and S installing the nozzle are always observed in the training process, the probability of using bicycle pump conditioned on installing the nozzle is higher. It leads the model to predict higher probability of Y conditioned on installing the nozzle when observing using bicycle pump. Then in the OOD task, inflate car tires, bicycle pump is absent, and the model may give wrong prediction. In causal inference, the intervention is formulated as do. Once one variable is intervened, its all incoming links are cut off, as shown. We intervene S with the backdoor criteria. However, the prior probability of Z is difficult to compute numerically, so we approximated it by the Monte Carlo method. We regard each step as an individual instance and put all the steps in a lottery box. Then we sample stats from it and assemble intervened videos where Z is not affected by S. The intervention helps to alleviate the negative effect of the context bias. Experimental results shows the effectiveness of our approach on both action segmentation and detection tasks. We visualize the results of our methods and the baselines, and the causal methods perform better. Thanks. Here is the QR code of our paper.